It's up to you if you wanna just stand or take a seat. So this will be our lab number 3. This is our last lab, but we have one demo remaining. So our lab for today is about the precipitation of lead phosphate and lead carbonate. So the objectives of these experiments are, first, is to investigate lead phosphate and lead carbonate precipitation, as well as dissolution reactions. And this will be done through the use of turbidity measurements for quantifying mineral precipitation rates. And then second is to use atomic absorption spectroscopy, or AES, to measure the dissolved lead in your solution. So phosphate has been added in some water treatment facilities in order to minimize calcium scale buildup, to control iron precipitation in water distribution systems, as well as to prevent some forms of iron pipe corrosion. So those mainly 3. And then in 1991, the EPA, or Environmental Protection Agency, right, has expanded the meaning of corrosion control to include lead and copper. So initially it was just about calcium and iron, but now they have to include lead and copper. And it states that if more than 10% of tap water samples exceed the action level, or the maximum permissible level of 1.3 milligram per liter for copper, and 0.015 milligram per liter for lead, then the water systems must undergo additional steps to control this corrosion. And in this case, phosphate can be added to water treatment facilities in order to prevent lead and copper release. And that's what we will study in this experiment, why we can add phosphate to treat lead. So more about lead. This is the EPA water standard for lead. It is called, it's one of the primary standards. So you have to really make sure that you meet the goal for this element. So the maximum contaminant level, which is defined as the highest level of a contaminant that is allowed in drinking water, for lead, use a specific treatment technique, and the action level, or the MCL, is 0.05 milligram per liter. That's in milligram per liter is ppm, right? Or it's equivalent to 15 ppb. Health effects of lead. For infants and children, it can delay physical or mental development. Children could show slight deficits in attention span and learning abilities. And for adults, can cause kidney problems as well as high blood pressure. What are the common sources of contaminant in drinking water, specifically for lead? Is the corrosion of household plumbing systems, especially those that were made before 1980s, and erosion of natural deposits in case of the source water for your for the source of water. So I believe everyone of you are aware with the lead in Flint water, right? So they call it, they have a water crisis. And the lead exceeded the maximum contaminant level of 15 ppb in some tap water, which started in 2014 up to present. And then the history behind this, initially they were getting their water from another city, Detroit, and then they wanted to save some money later on in the future. So they started to switch to another source of water, which is the Flint River water. So then, what are the causes of this high lead in their some of their tap waters? One is the source water itself has a high chloride level, and actually the chloride or chlorine can cause also corrosion. So here in this picture, this is from an organization called Flint Water Study.org. So what they did was they basically dipped a nail in the two sources. One is the previous source, the Detroit water, and then the other one is this Flint water. So they dip it for 1 month, and then after 1 month, that is the result. So this is the Flint water. It's really more corrosive. And basically, there's no corrosion inhibitor added here. And then they also, another cause of this high lead levels is increase in the amount of chlorine disinfectant. So actually, first is they had this E. coli and total coliform problem. So what they did is they increased the amount of chlorine disinfectant, and then later on they had two more problems. One is they had more chlorine disinfection byproducts in their water, and then there's this chloride corroding their pipes, compounded by the fact that they have, not everything, but they have service lines that are made from old lead pipe. So that's where's the lead coming from. And also, they failed to add corrosion inhibitor. Okay. So this is an example of a cross section of some of their pipes. Let's just turn off for a while. So this is the kind of corrosion that they're seeing in their pipes. So then last year they started to use orthophosphate as corrosion inhibitor. So why can we use phosphate as inhibitors? So first of all, phosphate corrosion inhibitors can be added in the form of phosphoric acid, just like the form that you have in soda. Your soda has a phosphoric acid. And also in the form of orthophosphate. Orthophosphate is this one, or polyphosphates. So the reaction of lead with phosphate, and in the presence of chlorine, or even chloride, or even fluoride and hydroxide, will produce this kind of salt. They call this pyromorphites, and if your anion here is chloride, then it's called chloropyromorphite. And so far, this mineral here has the lowest solubility and the most stable among all the forms of lead minerals. See, the log KSP is minus 84. And then compared with lead carbonate has a log solubility product constant of minus 13. So which is more soluble? Lead carbonate? Yes, right. So then once we form those precipitates, we will determine which one had the most or the more precipitate. Is it lead phosphate or lead carbonate? And when we add acid, which precipitate will dissolve more. And we will do that with the use of a turbidimeter. So turbidimeter measures turbidity, which is an optical property resulting from the interaction of light with suspended particles in solution. So when you have a particle and then you have a light, what happens is there's a lot of scattering, then there can also be absorption. So we will use a ratio turbidimeter. It's here. That's the turbidimeter, which measures the ratio of the light scattering at 90-degree angle of the incident light. So if this is your incident light, and then this is your sample, so these are all scattering, let's say, scattering then transmitted. So it will measure this, scattering at 90-degree angle, and then it will ratio it to the sum of the forward and transmitted light. And that's what it will give you. So the reason why a 90-degree angle is called nephelometric. That's why the unit for this is NTU, or nephelometric turbidity units. So it's a simple procedure. You measure the turbidity of standards. But of course, before that, before measuring the turbidity of samples, measure the turbidity of standards, which is, right now we have the latex standard, but it was calibrated with or standardized with a primary standard. What they normally use is a formazine. So that's the formazine is the #1 standard, but you can also use other standards as well as you calibrate it against formazine. So measure the sample of turbidity after 10 minutes of precipitation reaction and after addition of the acid. And then take note, if turbidity is greater than 199 NTU, because that one can measure up to 200. So there 0 to 2, 2 to 20, and then 20 to 200. But if turbidity is greater than 199 NTU, then you dilute a non-sample volume with an accurately measured filtered sample. So why do you need to dilute it with a filtered sample, not just like DI water? Because it may change. If you use DI water, it has a different pH. And actually here, you will be maintaining pH. So it may change. DI water may change may either dissolve your precipitate, or so it has a different chemistry than your original sample. So the next thing is, you take a sample, filter it using 0.2 micrometer filter, and then determine the dissolved lead in that filtrate. So when you say dissolve, actually the main meaning of dissolve is when you pass by a liquid sample in a 0.45 micrometer filter, whatever that passed through is called dissolve. So that's the #1 definition. But then these days, even a 0.2 micrometer, you can also consider as dissolved. So, but you have to specify which filter you use. In this experiment, we will use 0.2 micrometer filter, but still we will call dissolved. But then again, there's a complexity in that. These days, we have nanoparticles. You know, even those nanoparticles, if it's smaller than 0.2, it will go into your filtrate, and then it will still be called as part of your dissolved, substance. But in reality, they exist as particulate or nanoparticle. So then, we can call the lead in your filtrate as just total lead. Okay, so we will use AAS. Have you used AAS before? Okay, some of you. AAS is used to measure concentration of metallic gaseous atomic particles, and as well as some metalloids. And the basis is that these gaseous metals will absorb light, which cause energy transitions. And then, so it's like initially your atom is here, it will absorb light. The electron will jump off to higher energy transition. And then after that, it will go back and then the energy being released when it from the high energy to low energy will be transmitted to the detector, and that's the one that's measured by AES. In addition, each metal has a characteristic absorption wavelength. So this is different in when you measure compounds. Usually for compounds, you can use a spectrophotometer. So you can use a broader wavelength. But with elemental analysis, you use a very narrow wavelength. It's which is characteristic of each metal. So once again, it's used to measure the concentration of metallic elements such as cadmium, calcium, and so on, lead, and metalloids such as arsenic, silicon, boron, antimony in aqueous samples. Method detection limit, it can go from ppm to ppb levels, but it depends on each element. Each element will have a specific sensitivity with this instrument. The advantages, right now we only have halocathode lamps that can measure one element at a time. So that's a disadvantage. So if you want to measure 5 elements, you have to do one element each time. But they also sell halocathode lamps, which have different elements, but you will compromise sensitivity with that. Another disadvantage is the flame absorbs at wavelength of 250, less than 250 nanometer, wherein it will cause interference with arsenic, which absorbs at 193.7 nanometer in selenium. That's why when you want to analyze arsenic, you have to buy a separate module to connect it to AES because of this problem. You also will have matrix. Matrix is like where your sample is dissolved. Matrix interferences, ionization interferences. I will mention that on the next slide. And chemical interferences. So this is the process. You have a sample, basically in here, and then it will be aspirated by a tube into a nebulizer. The nebulizer is in here. So the purpose of the nebulizer is to basically create very fine mist of your sample. So it will create fine mist and then direct it to the burner, so where your flame is. So what happens to the flame? I will show you a video. The flame will be here. You can have two kinds of temperature. When you use a wide burner, just like this, you will be using an air acetylene to create your flame. And this is the temperature. It's 2100 to 2400 degrees Celsius. Then some elements will require a hotter temperature than that. And then you will have to use a nitrous oxide acetylene burner. And this is the temperature. So what happens in this high flame? Initially, the solvent in your matrix is evaporated. So you are left with your compound, but then your compound will be converted into the gas phase. So imagine initially calcium in the gas phase and then finally atomized. This is what we want for the AES. This is what the flame creates. But then, like I mentioned, there will be some ionization interferences. So in this temperature, some elements, you can still form some ionized atoms like this. So it's like, but you want more of the ground state. But if you have more of this, then it will create an interference. So then the ground state, so you have the ground state atom, right? Then you need a light beam source, which is the halocathode lamp. This is the halocathode lamp, which is focused through the flame. The ground state atoms will then absorb wavelength of light specific for that element. and then becomes excited, which means it's promoted to higher energy level. And then it doesn't remain there for long. It will come back to the ground state. Whatever energy is emitted there is transmitted to the monochromator and to the detector, and that's the one that measures the amount of light absorbed by the atoms. So I have a video here in case we won't make it. So that's the flame. Did you see? So you open your sample, let it be aspirated through the nebulizer. Oh, that was so quick. So initially your flame is blue, right? But then when you put your sample, the color of the flame will change based on what kind of elements are there. So if it's yellow, you know that some sodium atoms are there, and so on. And then there's another one. Yes, should have some. Okay, so if you click Analyze Sample, okay, so this is a real sample from our lab, from this experiment, and then it gave an absorbance reading of 0.097. So for AES, you must create. You will be given standards. The concentration is from 0.1 ppm to 10 ppm. But then when we tried, actually the limit of detection for that AES with lead is 0.4 ppm. So you have to create a standard calibration curve wherein you input your standard concentration here, and then this is the absorbance that you get from the instrument. You should have a linear curve, and then later on when you analyze your sample, you will get absorbance unit, right? Then you will determine the concentration based on that using this equation. So then if you have, for your results and discussion, this is what basically you need to fill in. You have the lead phosphate with the chloride in it, or it's called chloropyromorphite. Determine the turbidity after precipitation and after acid addition. And then determine the total lead in the filtrate. And you will do the same thing with the lead carbonate. So now the question is, in drinking water distribution pipes, chloride ions can exist. Can you explain why phosphate is added to immobilize lead? You should be able to explain that from this experiment. And so you have to wear your personal protective equipment, gloves, lab coat, and goggles. And take note, all your liquid sample waste will go to a bottle which is labeled hazardous waste, and then it will be collected by the EHLS. Never throw any liquid waste with lead in our sink. Wash hands with soap and water before you leave. And then you put it in your stir plate. basically you put your pH meter throughout the process because you will be maintaining it. So typically the pH, the requirement for the pH of tap water is from 6.5 to 8.5. Although they're not, it's part of the secondary standard, secondary standard for drinking water. That means it's not strictly enforced, but you know, they know that it should be within 6.5 to 8.5. So then you add your lead nitrate. This is lead nitrate. Just follow the specific volume recommended. So whatever tips you use, put it in a used pipette tip. We need to rinse that before we can throw in the trash. Then next we need to add sodium chloride as a source of our chloride ion. So let's say the pH right now is about, it's fluctuating 4.8, but I want weight, I will just add the rest. For you, you have to at least reach pH 6. So you want to add sodium hydroxide using 100 microliter increments until you have pH 6 here before you add your phosphate. So phosphate will be added in the form of phosphoric acid. So are you seeing any difference now? Okay, so from clear colorless, it forms some white precipitate, and then depending on the pH, it can be slow initially, and then but with some pH it's very fast. Once you add the phosphoric acid, you will see it. So now when you add phosphoric acid, the pH drops like 3, around 3. Then you have to immediately add sodium hydroxide to maintain the pH to 6. So after this is the one that you need to put in a turbidity vial. You fill this vial up to this, and then just insert it in this turbidimeter, and that's it, read the turbidity. But if it's outside the range, what you do is measure again a known volume of sample. Let's say get 5 ml, and then put 20 ml of your DI water, measure, and then just later on use your dilution factor to get the correct turbidity. So it's actually quick. And you will do the same thing for lead carbonate, but instead of adding the phosphoric acid, you will add the sodium carbonate.